A chip smaller than your palm just finished a calculation in under 5 minutes. The same calculation would take the fastest supercomputer on Earth roughly 10 septillion years. That's not a typo, and it's not an exaggeration. That number comes directly from Google's own research team. Stick around, because the real story behind this chip is stranger and more carefully documented than anything that needs embellishing. Let's start with the chip itself, because the name has already become well known. Willow is Google's latest quantum processor, built around 105 qubits. That number matters more than it might seem at first. And understanding why requires understanding what makes a qubit fundamentally different from anything. Inside a normal computer, classical computers, the ones you're using right now, run entirely on bits. Each bit is a simple switch, either a 0 or a 1. Every photo, video, message, calculation you've ever seen on a screen ultimately breaks down into enormous strings of these binary choices. Qubits don't work that way. Through a property called superposition, a qubit can exist in a combination of both states at once, rather than being locked into strictly 0 or strictly 1. And when multiple qubits become linked together through a phenomenon called entanglement, the resulting system can represent an enormous number of possible combinations simultaneously, rather than testing them one at a time the way a classical computer has to. That difference is exactly what made Willow's headline results so significant. Google ran Willow through something called a random circuit sampling benchmark, specific tests designed to measure how well a quantum processor can generate outputs from extremely complex quantum patterns. It's not a benchmark chosen because it's practically useful in daily life. It's chosen specifically because it's almost impossibly difficult for a classical computer to replicate. To put the scale of that difficulty in perspective, imagine being asked to count every single grain of sand on every beach on Earth, and then repeat that entire count over and over for a length of time longer than the universe itself has existed. That's roughly the scale of the task Google says a classical supercomputer would need to complete this specific benchmark. Willow completed it in under 5 minutes. This isn't the first time Google has made a headline-grabbing quantum claim. Back in 2019, the company announced a similar result using an earlier chip called Sycamore, claiming what researchers called quantum supremacy, a demonstration that a quantum computer had solved something no classical computer realistically could. That earlier claim faced real scientific pushback. Some researchers argued that better classical algorithms could eventually close much of that gap, given enough clever optimization. Willow's result feels different to many in the field, specifically because the scale of the gap involved isn't just large. It's astronomically larger, to the point where classical computing essentially looks like it's playing an entirely different kind of game. But the benchmark itself, impressive as it is, isn't really the most interesting part of this story. What's genuinely fascinating is the question Willow's performance forces scientists to confront. What is actually happening, physically, when a quantum computer performs a calculation like this? To understand why that question matters so much, it helps to understand one of the strangest, longest-running debates in modern physics. Quantum mechanics has always behaved strangely compared to the everyday world. A single particle can exist in multiple possible states simultaneously, only settling into one specific, definite outcome once it's actually measured or observed. For nearly a century, physicists have argued fiercely about what that actually means about the nature of reality itself. One major interpretation, often called the Copenhagen interpretation, treats those other possible states as purely mathematical tools, useful for calculating probabilities, but not physically real in any meaningful sense. Under this view, a quantum computer isn't drawing on anything beyond our own single universe. It's simply manipulating probability with extraordinary mathematical precision until the correct answer emerges. A different interpretation, called the many worlds interpretation, offers a genuinely more radical explanation. Instead of treating those other possible outcomes as simply vanishing once a measurement happens, many worlds argues that every possible outcome actually occurs, each one branching off into a separate, equally real version of reality that we, as observers stuck inside just one branch, can never directly perceive or interact with. Under that view, every quantum event effectively splits reality into multiple simultaneous branches. A particle goes left in one branch and right in another. A coin lands heads in one branch and tails in another. All of it real, all of it happening. just permanently separated from each other in a way we can't detect from inside any single branch. Now apply that specific idea to a machine like Willow. When Willow processes a calculation, it isn't testing one possibility after another sequentially, the way a classical computer would. It's manipulating an enormous number of possibilities essentially at once, using the quantum properties of superposition and entanglement across its 105 qubits. Under the many worlds interpretation specifically, those simultaneous possibilities being processed aren't just abstract mathematical placeholders. They potentially correspond to real, physically distinct branches of reality, with the final answer that appears in our specific branch emerging through a process called quantum interference, where different possible outcomes reinforce or cancel each other out until the correct pattern becomes overwhelmingly more likely to appear. If that interpretation is correct, then in some genuine physical sense, the computation isn't happening only inside the chip sitting in Google's lab. It's potentially distributed across the branching structure of reality itself, with an amount of computational work happening that no single classical universe, operating alone, could realistically complete on any comparable timescale. That's the exact idea that makes Willow's result feel genuinely mind-bending to a lot of physicists, rather than just impressively fast. Here's where it's important to slow down and be honest, though, because this is exactly where a lot of online coverage of this story runs wild with exaggeration. Willow did not prove that a multiverse exists. It did not detect another universe directly, did not send information across realities, and it did not receive any kind of message or signal from anywhere. The many worlds interpretation remains exactly that, one serious, long-debated interpretation of quantum mechanics, among several competing interpretations that all currently produce the exact same testable, verifiable predictions. The Copenhagen interpretation, still the most widely taught framework in physics education, doesn't require parallel universes at all to fully explain why quantum computers like Willow work the way they do. Under that interpretation, Willow isn't borrowing computational power from anywhere else, simply manipulating probability waves with a level of precision classical computers fundamentally cannot match. Until the correct interference pattern produces the right answer, both interpretations currently explain Willow's real, measured performance equally well, using entirely different underlying claims about what reality itself actually consists of. That's precisely why this debate has continued unresolved for nearly a century, and why a single benchmark result, however impressive, doesn't settle it on its own. There's more honest context worth adding here too. Willow's headline achievement involved a specific benchmark task. It's not a practical, real-world problem like designing a new drug, modeling climate systems, or breaking modern encryption. That doesn't make the result meaningless. But it does mean it's important to understand exactly what kind of milestone this actually represents. It demonstrates genuine, verified quantum advantage under a controlled, specifically designed test. It doesn't yet demonstrate everyday practical usefulness for the kinds of problems most people actually care about solving. There's also the ongoing challenge of scale. 105 qubits is genuinely impressive engineering, but many researchers believe truly practical, fault-tolerant quantum computing machines reliable enough to tackle complex real-world problems consistently may ultimately require systems with substantially more qubits than that. Quantum systems are also notoriously fragile. The slightest disturbance, a stray vibration, a tiny shift in temperature, even faint background electromagnetic interference can cause qubits to lose their delicate quantum state entirely before a calculation finishes, a problem researchers call decoherence. Building quantum computers has often been compared to trying to construct a cathedral out of smoke. The underlying theory is elegant, but the physical structure can collapse astonishingly easily. This is exactly why Google's progress on a specific separate part of Willow's announcement matters just as much as the headline benchmark speed, even though it received far less public attention. For years, one of the biggest open questions in quantum computing was whether adding more qubits to a system, specifically to help correct errors, would actually make error rates better, or whether it would simply introduce more opportunities for something to go wrong. With Willow, Google's team demonstrated that, as they scaled up the number of qubits dedicated to error correction, the system's overall error rate actually dropped exponentially, rather than increasing. That's a genuinely significant, practically important engineering milestone. It suggests a real, viable path toward eventually building larger, more stable quantum computers capable of tackling meaningful real-world problems, rather than remaining limited to specialized benchmark demonstrations designed primarily to showcase raw speed. If quantum computers can continue scaling up while simultaneously reducing their error rates, they gradually stop being fascinating laboratory curiosities and start becoming genuinely practical tools with real-world impact. Researchers are already excited about potential applications in drug discovery, where quantum computers could simulate complex molecular interactions far more efficiently than classical methods currently allow. Also in materials science, potentially helping design new materials atom by atom. And in climate modeling, potentially capturing levels of atmospheric and oceanic detail current classical supercomputers simply can't handle efficiently. There's also a more complicated side to that same coin: quantum computing's potential impact on modern encryption and cybersecurity. Since sufficiently advanced, reliable quantum computers could eventually threaten some of the cryptographic standards currently protecting digital information worldwide. A genuine area of active research and concern for computer security experts. None of those practical applications require resolving the many worlds debate first. The real-world value of continued quantum computing progress exists regardless of which interpretation of quantum mechanics eventually turns out to be correct, if either ever gets definitively settled at all. But it's worth sitting honestly with why this story captured so much public attention and generated so much genuine philosophical debate among physicists themselves, beyond just impressive raw numbers. For most of the century-long argument over how to interpret quantum mechanics, these questions largely remained philosophical, because the experiments physicists could actually run were simply too small and too limited in scope to force any kind of practical resolution one way or the other. A single quantum computer capable of performing a calculation so far beyond classical reach that the comparison becomes almost meaningless changes the scale of that conversation considerably. When a real, physical chip sitting in an actual laboratory performs calculations that classical supercomputers genuinely cannot replicate within any remotely comparable time frame, these previously abstract interpretive debates stop feeling purely theoretical. The machine itself becomes a tangible, physical question mark, sitting on a lab bench, quietly asking researchers what kind of underlying reality could actually allow a result like this to happen in the first place. Maybe the honest answer really is mathematical and probabilistic, exactly as the Copenhagen interpretation has argued for decades, with no parallel universes required at all. Maybe quantum computers are simply remarkably good at manipulating probability with a level of precision nothing else humanity has built can match. Or maybe, as many worlds proponents have argued for just as long, machines like Willow really are hinting that physical reality is genuinely larger and stranger than the single branch of experience we're each individually capable of perceiving directly. Either way, that's precisely why Willow feels different from simply being another entry in the ongoing competitive race between Google, IBM, Microsoft, and other companies pursuing quantum computing progress. It's a real physical result that makes a genuinely old, previously unresolved philosophical question about the fundamental nature of reality significantly harder to simply set aside as abstract speculation. So where does that honestly leave things right now in the summer of 2026? Willow's real, measured, independently scrutinized benchmark result stands on its own as a legitimate, significant technical achievement in quantum computing, regardless of which interpretation of quantum mechanics eventually proves correct. Its genuine progress on exponentially improving error correction as the system scales represents an equally significant, arguably more practically important milestone toward eventually building quantum computers capable of tackling real, meaningful problems beyond specialized benchmark tests. And the philosophical question its performance reopens whether quantum computation genuinely draws on some deeper, branching structure of reality itself, or whether it's simply an extraordinarily precise form of probability manipulation confined entirely to our own single universe, remains exactly as unresolved today as it's been for the better part of a century. Willow didn't answer that question. It made the question considerably harder to comfortably ignore. That's the real, complete, honestly caveated story behind Google's quantum AI, not confirmed proof of parallel universes. and not a fabricated claim dressed up to sound more dramatic than the underlying science actually supports. Just a genuinely remarkable piece of real hardware. Century-old, unresolved debate in physics that it's brought back into sharp, urgent focus, and an honest, ongoing scientific argument among serious researchers about what it might all actually mean. But there is another reason this technology matters, and it has very little to do with the multiverse. Quantum computing is ultimately about learning how to control nature at its most fundamental level. Instead of building machines that simply imitate physical systems using ordinary bits, researchers are trying to make the machine itself behave according to quantum mechanics and then use those properties to perform useful calculations. That distinction could become extremely important as these systems grow. Imagine trying to understand a molecule containing hundreds of interacting electrons. A classical computer can model that system, but the number of possible quantum states can become enormous extremely quickly. The computer has to approximate the behavior using mathematical shortcuts, because storing every possible interaction directly becomes impractical. A sufficiently capable quantum computer could approach the problem differently. The machine's own qubits naturally follow quantum rules, allowing researchers to represent aspects of molecular behavior directly within the quantum system. Instead of forcing a classical machine to calculate every possibility indirectly, the quantum processor could use its physical behavior as part of the calculation itself. That is why chemistry is one of the areas researchers watch so closely. A future quantum computer might help scientists understand how a particular drug molecule interacts with a protein, how catalysts behave during chemical reactions, or how electrons move through new materials. It could potentially help identify promising compounds before researchers spend years testing thousands of possibilities in laboratories. But that future machine does not exist yet. That distinction is important because quantum computing has often been surrounded by predictions that arrived decades before the hardware needed to support them. A benchmark result can prove that a quantum processor has achieved something remarkable without automatically meaning that commercially. Useful quantum applications are right around the corner. The engineering challenge remains enormous. Researchers have to control thousands, and eventually potentially millions, of individual quantum elements while keeping their error rates extraordinarily low. They need sophisticated cooling systems, control electronics, calibration procedures, error correction algorithms, and software capable of coordinating everything together. And unlike a classical computer, where replacing a faulty transistor is essentially invisible to the user, quantum systems have to constantly fight the environment itself. The universe is noisy. Temperature changes, electromagnetic radiation, vibrations, imperfections in materials. Even interactions between neighboring components can introduce errors into a calculation. That means the future of quantum computing may depend less on simply creating more qubits and much more on creating better qubits. If you want to keep following how this debate develops, as quantum computing keeps advancing, subscribe and turn on notifications. The real science here is genuinely strange enough on its own, without anyone needing to invent anything extra to make it interesting.